All right, let's jump right into this complete explainer on polygons. If you're studying Form 2 mathematics, consider this your ultimate Chapter 4 revision masterclass. We're going to treat this topic kind of like an architect's blueprint, giving you the exact tools you need to master these shapes, internalize their rules, and honestly, just completely crush your exams. Geometry really doesn't have to be intimidating when you break it down, and while that's exactly what we're going to do today.
To keep things perfectly organized, we'll build our knowledge step by step through 6 main sections. Meet the polygons, diagonals and symmetry rules, constructing regular polygons, the secrets of angles, step-by-step angle calculations, and finally, a summary with exam tips. Section 1. Meet the polygons. Let's establish exactly what our raw materials are.
Okay, so the most crucial point here is understanding the super strict qualifications for a shape to join this geometric club. The word itself, it comes from poly, meaning many, and gon, meaning angle. But the rules are strict. It literally must be two-dimensional, it has to be completely closed, meaning all lines connect, and it must be made exclusively of straight lines. So circles, out because of the curves. Open, unclosed shapes, definitely out. And 3D objects, instantly disqualified from being polygons.
And this perfectly illustrates the difference between our 2 main categories, regular and irregular. You can think of regular polygons as these perfectly balanced structures. Every single side is the exact same length, and every single interior angle is the exact same size. Irregular polygons, though, they're kind of the rebels. They have unequal side lengths and totally irregular angle sizes, which makes them just a bit more unpredictable. Now, this is basically your ultimate visual cheat sheet for matching names to the number of sides. You probably already know the triangle with 3 sides or the quadrilateral with 4, right? But you really need to commit the rest to memory. Pentagon for 5, hexagon for 6, heptagon for 7, octagon for 8, nonagon for 9, and decagon for 10. And what about when we don't know the exact number of sides? Well, we just call it an n-gon, where n stands for that unknown number.
Moving on to Section 2. Diagonals and symmetry rules. Let's uncover those hidden lines. So, a diagonal is just a straight line connecting 2 non-adjacent corners. But let's say you have a shape with 20 sides. You definitely don't want to be drawing and counting those lines manually. Instead of guessing, you can use this simple algebraic formula to find out exactly how many diagonals cross through any polygon. It's 1/2 n multiplied by n minus 3. So for a triangle where n is 3, the math gives us exactly 0 diagonals. For a quadrilateral, it gives us 2. And for a pentagon, just plug in 5 for n, and you perfectly calculate 5 diagonals every single time. It's like magic. Now for symmetry. This is a line through a shape that creates perfect mirror images on either side. Regular polygons make this incredibly easy because the number of lines of symmetry simply equals the number of sides. A regular equilateral triangle has 3, a perfect square has 4, boom, done. But irregular polygons, they force us to use the folding method. You literally have to mentally fold the shape to see if the sides match up. For example, an isosceles triangle has only 1 line of symmetry, while a scalenes triangle has absolutely 0. Section 3. Constructing regular polygons. Time to break out the geometry tools. Let's actually construct an equilateral triangle with 5 centimeter sides. First, draw a flat baseline segment. Let's call it AB, exactly 5 centimeters long. Next, take your compass, set the radius to 5 centimeters, place the point right at A, and draw a curve above the line. Then, without changing that compass setting at all, move over to point B and draw another curve to intersect the first one. That intersection right there, that's point C. By following these exact steps and connecting A and B to C, you guarantee all 3 sides are perfectly equal. And you didn't even need to touch a protractor. All right, let's step it up and construct a regular hexagon with 3.5 centimeter sides. First, draw a complete circle with a 3.5 centimeter radius. Mark any point on the edge and call it A. Keep your compass set to 3.5 centimeters, place the point on A, and strike a curve on the circle's edge to find point B. Now, just move your compass to B and strike the next curve for C. I absolutely love this method, because building a perfect 6-sided hexagon is essentially just walking your compass step by step around the circumference of a circle until you reach point F. Then you just connect the dots with straight lines. Section 4. The secrets of angles. Time to unlock some serious mathematical power. So the absolute golden rule to remember here, like the total foundation of polygon angle calculation, is the number 180. an interior angle, the one inside the shape, and its adjacent exterior angle, which is formed by extending one of the sides outward, they always sit on a perfectly straight line. And because they sit on a straight line, they're supplementary. This means they will always, without fail, add up to exactly 180 degrees. If you know one, you instantly know the other. Simple as that. To find the total internal angles of any polygon combined, we use this brilliant formula. N minus 2 multiplied by 180 degrees. Now what this formula is actually doing is subtracting 2 from the number of sides, which cleverly tells you exactly how many triangles can fit inside that polygon. Since every single triangle contains 180 degrees, you just multiply that number of triangles by 100. So for a 6-sided hexagon, 6 minus 2 is 4 triangles. 4 times 100 gives us a total interior sum of 720 degrees. Pretty cool, right?
Okay, prepare yourself for one of the most elegant constants in all of mathematics. Regardless of whether your polygon has 3 sides, 13 sides, or 3,000 sides, the total sum of all its exterior outside angles will perfectly lock in at 360 degrees. Always, no exceptions. And if it's a regular polygon, you can even find the exact size of a single exterior angle just by taking that magical 360 and dividing it by the total number of sides.
Section 5, Step-by-Step Angle Calculations. Let's put these formulas to work. This right here is a classic mystery you'll definitely face on a test. Imagine you have a 5-sided irregular pentagon. 4 of the interior angles are given, 100, 130, 60, and 90 degrees. That 5th angle, it's simply labeled X. So the big question is, how do we systematically deduce the identity of this missing angle X?
Well, by breaking it down into these 3 actionable steps, the algebra becomes incredibly straightforward, like impossible to mess up. Step 1, figure out what the total sum should be. It's a 5-sided shape, so 5 minus 2 is 3, and 3 times 180 gives us 540 degrees. Step 2, add up the angles we already know. 100 plus 130 plus 60 plus 90 equals 380 degrees. Step 3, take our total required sum of 540 and subtract that known 380. That leaves us with exactly 160 degrees. Boom! X is 160 degrees, mystery solved.
Now here's the trick teachers will inevitably test you on, working backward. Instead of giving you the sides and asking for the angle, they give you a single interior angle, in this case 108 degrees, and ask you to figure out exactly how many sides the entire shape has. Using the exterior angle as a shortcut is a really brilliant strategy here. If we know the interior angle is 108, we just use our 180-degree straight line rule, right? 180 minus 108 means the exterior angle must be 72 degrees. Because it's a regular polygon and we know all exterior angles always total 360 degrees, dividing that global 360 by our single exterior angle of 72 quickly reveals the answer. 360 divided by 72 equals 5. We are absolutely looking at a 5-sided regular pentagon. Trust me, it is so much faster than trying to reverse engineer that whole interior angle formula.
Section 6, Summary and Exam Tips. Let's build your ultimate polygon toolkit.
Seriously, memorize this. It condenses every single concept we just learned into a powerful toolkit that's going to help you solve any polygon problem thrown your way. You've got your diagonals formula to find those hidden structural lines. You have the interior sum formula, n minus 2 times 180, to find the total inside angles. You have the golden 180-degree rule linking interior and exterior angles. You've got the unchangeable 360-degree exterior sum. And of course, you know how to calculate a specific regular interior angle. This right here is your absolute armor for Chapter 4. So armed with these geometric blueprints, I want to leave you with a provocative thought. Where can you spot perfectly constructed regular polygons hiding in the architecture of the real world today? Because once you start looking, they're everywhere. From the incredibly perfect hexagonal honeycombs built by bees to the massive steel trusses holding up the bridges in your city. Polygons aren't just abstract shapes in a math textbook. They are literally the foundational structural language of our universe. Keep your eyes open, keep practicing those formulas, and you will absolutely ace this math exam. Catch you in the next explainer.